Okay, so now that you've done percent composition, okay, we're going to kind of do the reverse process of that with what's called empirical formula. Okay, so empirical formula, another word for that is simplest formula, but what we're going to look at in this podcast will be how to actually create formulas. Okay, now one of the things that we're going to do though is I'm actually going to break down a formula here, and we're going to look at what is the actual meaning of a formula. So go ahead and write the formula for iron 2 chromate. And that formula should be FeCrO4. Now, one of the things I want to make sure that we truly understand is what exactly does a formula mean. And if we break this formula down, okay, we have 1 atom of iron, 1 atom of chromium, and 4 atoms of oxygen. Okay, so that's what this formula actually means. Okay, I have 1 of these, 1 of those, and 4 oxygens. Now, if I take this and I scale this up, okay, this ratio is basically for these atoms is 1 to 1 to 4. That's the atom ratio. Well, if I scale this up, if I had 10 atoms of Fe, how many atoms of chromium would I need? And then assuming you would say 10, because that's the 1 to 1 ratio. And how many atoms of oxygen would you need? And hopefully you would say 40 atoms of oxygen. Okay, well if I scale this up even more to 100 atoms of Fe, how many atoms of chromium would I need? Well, it would be 100. And how many atoms of oxygen? And hopefully you're saying 400. Well, what if I really got all wild and crazy and I scaled this up to 6.022 times 10 to the 23rd atoms of iron? In a 1 to 1 ratio, how many atoms of chromium would I need? Well, I need the same amount, so I need 6.022 times 10 to the 23rd. And how many atoms of oxygen would I need? Well, I don't really feel like doing the math, but I would need 4 times 6.022 times 10 to the 23rd. So I need 4 times that amount. Well, this number is also called a, besides Avogadro's number, it's a mole. So, and it happens to be 1 mole. So 1 mole of Fe would need 1 mole of chromium and 4 moles of oxygen. So now, you see why these moles actually become important is we can count large numbers of atoms with those. And what happens is, with those moles, okay, chemical formulas can represent atom ratios or mole ratios. And that's what we want to look at them in terms of, in this particular section, is we want to look at chemical formulas being in terms of a mole ratio. So back to this means there's 1 mole of Fe for every 1 mole of chromium for every 4 moles of oxygen. That's our mole ratio instead of being atoms. Now, how are we going to use that? Well, we're going to look at something called empirical formula. Empirical formula also goes by the name simplest formula. And the textbooky definition of simplest formula is this right here. The simplest formula of a compound is the smallest set of possible whole numbers for the atoms in a compound. Okay? So that's the simplest formula. Now, we've actually kind of done this, okay? When I've given you some compounds and I've said, okay, you have Cu2 Br4. Okay, but when you've had that in a formula, I've asked you to reduce that to CuBr2. Okay, well, this is the simplest formula. And so we've kind of already done this to some extent. Now, what we're going to do is we're going to look at these simplest formulas in terms of moles, and we're in particular in terms of ratio of moles. Now, it is best just to start this by looking at a problem. Okay, so I want to see this problem copied in your notebooks. I'm going to keep talking, so you might want to pause the video to write this problem down. But you need to have this problem written in your notebooks. It will be something that I will look for. So notice I have these percents. Okay, so that's kind of why we did percent composition in the last compound, in the last example. VodCast, that's the word I was looking for. So I have 69% of this compound is barium, 6% is carbon, 24% is oxygen. And what we want to do is, from that, determine the simplest formula. There are 4 basic steps, and I want you to write down all the directions for each step. Here is the first step, okay? Because the percents should all add up to be 100%, what we're going to do is say, well, if I have 100% of a substance, I'm going to say I have 100 grams of that substance. Okay? So basically what you're going to do is, whenever you see percents, we are going to change the percents into grams. So if I have 69.5% barium, if I had 100 grams of this compound, that would mean 69.58 grams of this compound is barium. If this compound was 6.09% carbon, and I had 100 grams of it, that would mean that I have 6.090 grams of carbon. And the last one, if I had 24.32% oxygen, that would mean I have 24.32 grams of oxygen. Okay? So that's our first thing. You're going to change your percents to grams. Step 2. Okay? Now what you're going to do is you're going to calculate the moles of each substance by using the molar mass. Okay? Molar mass comes from the periodic table. That's where you're going to get the molar mass from. And you're just going to use the molar mass of the elements. Okay? And what you want to do in this calculation is you don't want to cut it off too soon. Okay? So you're better off carrying more decimal places than not. So carry 3 decimal places with this. So I'm going to go to the periodic table and I'm going to find the molar mass of barium. And you look on the periodic table, the molar mass of barium is 137.3 grams. So 1 mole of barium is 137.3 grams. So what I'm doing is I'm just making a conversion where I'm converting grams to moles. And this is what you did in the very first VodCast. We converted grams to moles. Okay? In fact, this is simpler because we're just using one particular element. Okay? So when I do that, grams cancel, and this comes out to be 0.507 moles of barium. Okay? We're going to do that with all of these. So I'm going to do the same thing with carbon. I'm going to look up, and 1 mole of carbon is 12 grams. The grams cancel. So this is going to come out to be 0.507 moles of carbon. And then the last one is oxygen. So 1 mole of oxygen is 16 grams. And that comes out to be 1.52 moles of oxygen. Okay, so now here's the thing. These moles right here are my mole ratios, okay? So what this really means is, in my compound, I have barium, carbon, and oxygen, okay? But I have 0.507 moles of this barium, and I have 0.507 moles of this oxygen, and I have, or carbon, and I have 1.52 moles of the oxygen. Now, these are not real easy numbers to work with, and if you go back to the original question or statement of empirical formula, it's the smallest set of possible whole numbers. Okay? So what we're going to do in our third step is this. We are going to divide each of these numbers by the smallest number of moles. Okay? So we're going to divide each number by the smallest number of moles. Now I'm going to show you the way I do this. Okay? For easiness purposes, I actually use this particular setup right here. And if you set this up on your paper like this, I think it's the easiest way, because now I have all of these moles sitting in front of me, and what I want to do according to rule 3 is I want to divide all of these by the smallest number, and the smallest number is a tie between this one and this one, so it doesn't really matter which one I choose then. So I'm going to divide all of these by 0.507. Okay? Now, unfortunately, I don't have very much room here, okay, to do this. So I'm going to split a screen here. I don't like that. Okay? So what should happen then is, I'm going to rewrite these just so I have it. So I have 0.507 divided by 0.507 moles of Ba, and that equals 1 mole of Ba. And I had 0.507 moles of carbon divided by 0.507, and that is 1 mole of carbon. Okay, and then I had 1.52 moles of oxygen divided by 0.507, and that turned out to be 3 moles of oxygen. Okay? Now, what I want to do in my last step is I want to write the simplest formula using these now smallest numbers. Okay? So what I have is 1 mole of barium to 1 mole of carbon to 3 moles of oxygen. So what that's going to turn out to be then is I have BaCO3. These numbers here change into subscripts, but we never write the subscript 1. Okay? So there is my formula. So basically what we have done is we've reversed the process of percent composition. Okay? When we calculated percent composition, we took these elements and found the percent of each one. Now what we did was we started with the percents, and we now found out what the formula was. Okay? So we're going to do another problem here, another example. And if you're one of those people that gets something the first time, I would fast forward and look at the next example that I'm going to do, just so you see one other thing that can happen, okay? So, if you're a person that needs to see more examples, here's another example, and I'm going to run through this, how you should really set it up on your page, and we're going to follow the steps, okay? So, on one line, our first step is to change the percents to grams. So, 29.1% sodium is 29.1 grams of Na, and we're going to do a T-box with that, so leave yourself some room when you write down sulfur, okay? So I'm going to go down a little bit on my page, and I'm going to change the 40.5% sulfur to 40.5 grams of sulfur. And in my next step, we're going to do a T-box with that, so I'm going to leave that. And then we're going to do 30.4 grams of oxygen. Okay, so that was step one. Step two then is to change the grams to moles by multiplying by the molar mass. So we're going to multiply by the molar mass of sodium. 1 mole of sodium off of the periodic table is 22.9 grams. Hopefully you understand where we're getting that number. 1 mole of sulfur is 32.1 grams. And then 1 mole of oxygen is 16 grams. And again, those molar masses are just coming off the periodic table. Those are the masses in the periodic table. Okay, so this then comes out to be 1.2707 moles of Na. This comes out to be 1.261 moles of sulfur, and this one comes out to be 1.9 moles of oxygen. Okay? Now, step 3. Okay? This was step 1, change grams to moles. This was step 2, change percents to grams. Step 2 is change grams to moles. Step 3, remember, is to divide by the smallest one. Now the smallest one happens to be 1.261, so that gives me 1 mole of sulfur. I know this doesn't come out to be exact, but 1.1 or something like that is still 1 mole of Na. Sorry about writing that poorly. And then this last one, though, 1.261, that actually comes out to be 1.5 moles of oxygen. Okay? So great. Here's what happened. I divided by my smallest number, but I did not get an even number. Okay? If you look at what we have right now, and we have 1 mole of Na, we have 1 mole of sulfur, and we have 1.5 moles of oxygen. Okay, I cannot write a formula that says NaSO 1.5. That just doesn't exist. So here's what you have to do, okay? Whenever you have an odd number like 1.5 or something like that, you are going to have to take this whole works times 2. Okay? So that means I have 2 NAs, 2 sulfurs, and 3 oxygens. Now I have my whole numbers, so now I can write my formula. Na2S2O3. Okay? one other thing that can happen to you. Okay? One last thing that could happen is you could be given mass right away. Okay? And if you're given mass right away, then what you want to do is you don't have to convert. You can just take these masses and work with them. So you can take 7.2 grams of carbon and you can set up and go change those to moles. And you can take the 1.2 grams of hydrogen and you can go on and you can take the 9.6 grams of oxygen and you can go on. Okay? So if you're given grams right away, then you don't have to worry about the percents. You just take the grams and you go. Okay? So from here, okay, your assignment is the simplest empirical formula worksheet.